Hello everyone, welcome to the first video of 10 AP Physics 1 summaries. Today we'll be looking at the Kinematics unit and focusing on conceptual review. If at the end of this video you're looking for more resources, please check out my description down below for links on more concept review and application problems. If you want to target your time towards specific content areas, I will include timestamps in the comments for each topic. Let's get started. So before we look at the key concepts of kinematics, it's important that we know what it is. You will not be assessed on this, but it is helpful to know nonetheless. It's defined as the study of the motion of points, objects, and groups of objects without considering the causes of its motion. Here we have one example, which is a dot diagram, also sometimes called a ticker tape diagram, where we can observe an object's motion based off of the relative distance of dots recorded at regular time intervals. These are often used in kinematics lab procedures because they give insight into the motion of objects without directly reflecting the cause of it. This video will extend a little bit beyond kinematics because of how the AP curriculum is organized, but we'll mostly be looking at displacement, velocity, and acceleration through the kinematics lens. The first major concept we see is the differentiation between vector and scalar quantities. You've likely seen this before, but a vector quantity is something with both magnitude and direction, whereas a scalar quantity only has magnitude. They're called vector quantities because they are represented by vectors, these arrows. The length reflects the relative size, and the head of the arrow points in the direction of the quantity. Conversely, if you can describe every aspect of the measurement with an integer, it's likely a scalar measurement, something like 2 kilograms. I'm using the absolute value symbol for scalar to indicate that it is magnitude only. We generally work with vector quantities in physics because direction plays a major role in physical interactions. It's important to be specific between the two. If we're talking about vector quantities, we have to understand reference frames. Let's start with an example. This is Peter. Peter is observing a car drive down the street with some non-zero velocity in this direction. Now, this is Jessie. Jessie is observing the same car, however she is taking a run down the street with the same velocity as the car. Peter and Jessie are observing the same car have different velocities because it is in two different reference frames. We have to choose appropriate reference frames, otherwise it can be misleading, such as Jessie saying that the car has 0 velocity, although it is relative to her. To have direction, you must have something else to refer to, even if it's as simple as a Cartesian plane. Otherwise, describing the motion of a system is confusing and unspecific. We'll see more on this later, but the idea of relative motion is central to your understanding of systems. So what motion are we describing? We're going to focus on vector quantities, starting with displacement. This is a change in position. If I run in a circle and stop where I started, I may have run a distance equal to the circumference of the circle, but I have 0 displacement. Displacement only cares about where you start and stop. It also necessitates a direction. For example, if I move from x equals 0 to x equals 3 along a number line, I moved 3 units in the positive direction. You could also say I moved negative 3 units in the negative direction, although this would be weird. After displacement, we have velocity. This is the rate of change in displacement with respect to time. For example, I could run 3 meters per second east. Next, we have acceleration, which is the rate of change of velocity with respect to time, like accelerating 1 meter per second eastward. Each level of this is the rate of change of the one before it with respect to time. When we talk about velocity and acceleration, it's important that we distinguish between instantaneous and average. A projectile's average velocity will be different than its many instantaneous velocities. You can imagine instantaneous velocity as the value you would record if you monitored the motion with a sensor and went back to the velocity at a specific moment in time. On the other hand, for average values, you can imagine recording an object's path and time and doing the calculations from total time and total distance. For these totals, we use delta notation. This little triangle indicates that you're subtracting the final value from the initial value for the change. When we calculate average velocity, we use delta displacement over delta time. Similarly, for acceleration, it's delta velocity over delta time. If we instead want instantaneous values, we have to be able to calculate or observe them at specific moments in time. Okay, now for the moment we've all been waiting for. Here are the big equations this chapter uses. You can of course memorize them if you want, and I would even suggest you do so for exam timing. However, it will make your life a lot easier if you develop a personalized understanding of where they come from. The first way to check if you understand them is to try to say them out loud. I do not mean literally v final equals, etc. I personally think along the lines of, if I had to prove these are true, where would I start? I read these equations respectively as the final velocity is equal to the initial velocity plus the velocity gained by some constant acceleration over time. The final displacement is equal to the initial displacement plus the displacement gained by the initial velocity over time plus the initial displacement gained by the changing velocity over the time. And then lastly, the final velocity squared is equal to the initial velocity squared plus twice the constant acceleration times the distance it occurred over. Now let's break them down. This one is the most self-explanatory in my opinion. If we want to know the final velocity after acceleration has occurred, we want to know what velocity it started at and how much it changed. If we focus on a times t, and we know that acceleration is the rate of velocity change over time, or delta v over t, when we multiply this rate by the time, we get delta v, which is, by definition, the change. Once we add the initial and the change, then we should get the final. Another helpful tool to understand equations and verify that they hold true is unit analysis. If we represent every value in this equation with its units and then simplify, we should get a valid statement. When we're building our physics intuition, it helps to look at equation to word equivalence, units, and then what changes are happening. On to the next one. This one looks a little intimidating at first glance, but once you recognize that each addend on the right side represents some additional form of displacement, it makes more sense. Units again, check out. So now we're looking for final displacement. We start with adding the initial displacement. Then we add the displacement that is gained from whatever the initial velocity is over the length of time we're considering, which is right here. This last term is where it gets a little bit more complicated. Similar to the one before it, it shows the additional displacement that occurs because of motion. However, here we focus on acceleration. If we instead think of a times t squared as delta v times t, we get a similar term as the one before it. This makes sense because v times t gives you displacement. The tricky thing here is the 1/2. For ease, I'm going to consider a situation with a positive acceleration. From here, I think of 1/2 as the constant that averages the additional displacement you would have if you started at the high final velocity with the additional displacement you would have if you stayed at the lower initial. Since it's speeding up, the rate that it's gaining displacement is increasing. Therefore, we have the 1/2 constant to account for this increasing rate. This final term ends up adding the additional displacement from the acceleration. If this doesn't make intuitive sense right now, don't worry about it. This is how I mentally break down the equation, but it's important that you find a way that makes sense for you. In the meantime, let's move on to the final major equation for this unit. This one also looks challenging, so let's make sense of it. Units again make sense. Feel free to do this for yourself if it helps. To give you some context, you can derive this equation from isolating t in our first equation and plugging it into our second. I would recommend familiarizing yourself with this form though for timing's sake, but know that you can derive it just fine. When I look at this equation, my brain goes to Pythagorean. If we focus in on this last term right here, the one that usually gives us the most trouble, we can see that it essentially gives us another velocity squared term. First, recognize that acceleration is delta v over t. If we use the commutative property and remove the 1 over t away from the delta v and over to the delta x right here, when we multiply a times delta x, we can create the equivalent of two velocity factors, one being delta v and the other one being delta x over t, which is also known as v. At its core, this equation has all velocity squared terms. This is helpful to recognize because it makes each term more concrete. Again, find a way to break these equations down for yourself because manipulating and simplifying them solidifies your personal conceptual understanding. Lastly, I want to touch on center of mass. You've probably heard of this outside of physics, often related to balancing in sports. It's the average location of the mass in an object or a system. This comes up frequently because we usually treat objects and systems as point masses. This theoretical model allows us to visualize interaction and motion in a very simplified way while ignoring the more complicated aspects of internal structure that come with bigger objects. Note that any time we reference an object's displacement, velocity, or acceleration, we are actually referencing the displacement, velocity, or acceleration of its center of mass. If we have objects whose mass is uniformly distributed, its center of mass is at its centroid or geometric center, which would be right here, right here. There's not always literal mass at this location like this hoop, but still if we were to average all of the locations, it would be at its center. If the object is not uniformly dense, the center of mass is usually not at its geometric center. Imagine a bar that is way denser on one side, like this over here. Its average mass distribution would be closer to the denser end. Alright, we made it. In my next video, we'll move on to dynamics. Thank you so much for watching, and be sure to check out the description for more resources and more about me. I'll catch you in the next one for more AP Physics 1 content.